Okay, number 16 is another inverse function. So again, the idea on inverse functions, we want to swap out our x's and our y's. So this f of x becomes x equals, and then replace both of those x's with y's. We then need to solve for that y. First thing we have to do to solve is to get this out of the denominator. We can't solve for anything that's trapped at the denominator. So I'm going to multiply both sides of my equation here by 2y minus 5. On the left-hand side, I'll go ahead and distribute that x in. So we get 2xy minus 5x. On the right-hand side, those two cancel. Nice, we get 3y plus 4. So that was step one, get rid of that fraction. Next up, if we are solving for y, all the y's have to be in the same place. So we want to add and subtract to move our terms around to get anything with a y on one side and anything without a y on the other side. So I'm going to subtract this 3y on both sides. While I do that, I'm also going to add this 5x. So I want anything with a y on the left, anything without a y on the right. So what I have then, these two cancel each other out. Over here, I'm left with 2xy minus 3y. And these two cancel each other out. I'm left with 4 plus 5x. Again, keep in mind, I'm solving for y. Right now, y is showing up in two separate terms. I can't solve for it when it's in two different places, so I want to factor it out front. And our final step there, we have y times the quantity 2x minus 3. So to solve for y, we're going to divide both sides by that entire quantity. So we end up with y equals, over here they cancel, 4 plus 5x over 2x minus 3. Or if we want to write that in our inverse notation, that is f inverse of x is equal to 4 plus 5x over 2x minus 3. Number 17. They gave us a quadratic equation here, and the first thing they want us to do is change that into vertex form, and then we also want to graph that function. So there's two different ways we can go from this sort of general form into vertex form. You can do some completing the square type of operation, but I prefer really just to use our little vertex formula. H is negative b over 2a, and k is then f of h. H being the x value of our vertex and k being the y value of our vertex. Remember, a vertex is a point, so it's an ordered pair. So here we have the negative sign from our formula, and b is negative 6, so we have two negatives up top. 2 times a is 3. So minus a negative 6 becomes positive. 6 over 6 is 1. That's the x value of our vertex. We then take that number and we plug it into our function for x. We get 3 times 1 squared minus 6 times 1 minus 4, which is what? 3 minus 6 is negative 3 minus 4 is negative 7. So we now know that our vertex is at the point 1, negative 7. That's going to help us when we go to graph. And we can now write in vertex form. Our function is f of x equals a. A is the same in either form, so it's still going to be 3 because that's what it was here, times x minus h squared. Don't forget that exponent. I have people do that a lot, and that's what makes it a quadratic. We need to make sure it is squared, plus k. Our k is negative 7. We would want to go ahead and simplify that double negative, so our final answer would be 3 times x minus, sorry, not double negative, double sign, plus a negative 7 is the same as minus 7. There is our equation in vertex form. Now, when we go to graph this, we do have our vertex. It is positive 1, negative 7. So that's our vertex right there. I know this parabola is going to be facing upward because a is positive, a is 3. So I do need some more points. We could factor to find the x-intercepts. We can find the y-intercept. We can make a t-table. We have a lot of options here. I think I'm going to stop with the y-intercept because that's a real easy point to find. That's a nice, almost freebie. We put in 0 for x. We get 3 times 0 squared minus 6 times 0 minus 4, and that is negative 4. So the point 0, negative 4 is on our graph. Because every quadratic, every parabola has an axis of symmetry, that's that sort of imaginary dashed line that runs down the middle. That means I know that I have to have a point on the other side of my axis of symmetry, so that one y-intercept really gives me 2 points. And maybe just for good measure, we should have one more x value. Let's try x equals negative 1 and see what that point is. 3 times negative 1 squared minus 6 times negative 1 minus 4. That is 3 plus 6 minus 4, or 9 minus 4, which is 5. Negative 1, positive 5 here. And again, because of that axis of symmetry, I know I have to have a point 2 units to the right of that imaginary line. So that gives us a great setup for graphing our nice little parabola. As smooth as you can make it. There we go. Number 18, we are given a polynomial function and we have two things to do. We need to find x values where that function is positive and x values where that function is negative. And then we also need to sketch the graph of the polynomial. So I'm going to start with this part. When we need to sketch the graph of a polynomial function, the most important points that we could find are the zeros or the x-intercepts of that function. So we want to solve this equation right here for x. Since we have 4 terms there, I'm going to try factor by grouping. I can pull an x squared out of the first 2 terms. And the last 2 don't have an obvious common factor. So since that leading term is negative, I'm going to factor out a negative 1. And that becomes x plus 4. Looking good because now these 2 match. So that becomes our GCF, our greatest common factor. We pull that single x plus 4 to the front. And what's left behind is x squared minus 1, which we can factor one more time. And so we have 4 zeros or 4 x-intercepts. We have one at negative 4, positive 1, and negative 1. And I'm just going to go ahead and graph those points. We need them negative 4, negative 1, and positive 1. Next up, what I like to look at is our end behavior. We do that leading coefficient test. The leading coefficient is our coefficient with the highest degree, the highest exponent. And we look at 2 things. Is that exponent even or odd? In this case, it is odd because it is x cubed. And is the coefficient of that term positive or negative? And here it's positive because it's a positive 1 is the coefficient. Whenever we have odd and positive, our end behavior is we are going down to the left and up to the right. So if we translate to that to our x-intercepts that we have over here, we're going down on this side and up on that side. And what's happening in the middle? Well, look back at these x-intercepts or zeros. Each one of these came from a factor that was only raised to the first power, doesn't have an exponent, which means it is raised to the first power, which means each one of these values has a multiplicity of 1. So at each of those x-intercepts, we are going to be crossing the y-axis, sorry, x-axis. So we cross there, we cross there, we cross there. This is just a rough sketch. If I were to draw this more precisely, maybe I should, I would have gotten that y-intercept is actually negative 4. So we would go all the way down to that point. I don't really know how high this bump in the middle is going. These are just rough sketches, not precise graphs. So you just want to get an idea of what's going on. So there's our graph. Then we still need to answer, where is our function greater than 0, meaning positive? So our function is 0 right here on the x-axis at those points we just found, our x-intercepts. It is positive or greater than 0 anywhere it is above that line. So for this particular curve, it's here and it's here. And we want to use x values to show where that highlighted area begins and ends. So this first one, there were our x-intercepts. The first highlighted area begins at negative 4. and continues to -1. That whole part is above the x-axis. And then the second highlighted area starts at 1 and it stays above for the rest of the curve. So those are the intervals where the x values that give us a positive result from our function. And where is our function negative or below that axis? Here and here. Again, we use our x values to show where those areas begin and end. So it's below the x-axis or negative from -infinity to -4. And it is also below the x-axis from -1 to 1. Some things to check for. You should never have the same interval in both of these answers because something cannot be both positive and negative at the same time. So you wouldn't have -4, -1 on both of these lists. Another thing to look for is the values that begin and end your intervals should always be your x-intercepts because that's going to be the point where we change signs. Okay, number 19. Another one. This time, well, this is nice. It is factored for us already. So we are ready to go in and just figure out what those x-intercepts are. So we are factored 0 equals -x cubed, x minus 5, and x plus 3 squared. Hey, first one, this one, when we set -x cubed equal to 0, divide both sides by -1, take the cube root of both sides, it doesn't matter. We still end up with x equals 0 for one of our intercepts. Notice this came from a factor that was raised to the third power. So this intercept has a multiplicity of 3. Since it's an odd number, that means we are going to cross the axis at that point. Our next one, we get an x-intercept of +5. This came from a factor with no exponent, which means basically it has an exponent of 1. So this one has a multiplicity of 1, also odd. So we are also going to cross the x-axis at that point. And then our last factor, we get our intercept of -3. This one came from a factor that was squared. So this one has a multiplicity of 2. Even multiplicity. So at that point, we're not going to cross the axis. We're just going to touch or bounce off of it. Okay, so let's plot those intercepts. We have one at 0, one at 5, and one at -3. We can't use our multiplicities yet because we need to know our end behavior. We have to do that leading coefficient test. Here, it's a little bit trickier with our leading coefficient. We're going to have to add up all these exponents so we can know what our degree is. So we have x cubed times x squared. 3 plus 2 plus 1, that is 6. So that is an even degree function. And then we have to look. Here we would have a negative times a positive x times a positive x. So our leading term is going to be negative, okay? Even and negative means that both tails are going to be facing down. So that means the tail to the left has to be down and the tail to the right has to be down. And what's happening in between? Well, this is the point x equals -3. That is where we are going to touch. So we touch the x-axis and come right back down. Now, our only choice next is to go to 0. You have to connect your intercepts in order from smallest to biggest. At 0, we are going to cross the x-axis. That one had an odd multiplicity. And then we have to come to this one, and hopefully that was a cross, and it was, so that works out. It's kind of a bumpy curve. Should be a little smoother if I drew it well, but you get the idea. We are just looking for a rough sketch here of our graph. Let me fix that just a little bit. Good enough. There we go. Now, we want to answer that last question again. Which intervals is our function positive, and in which intervals is our function negative? Positive is where are we above the x-axis, and this is the only one. There's only one positive interval from 0 to 5. The rest of the intervals are all down here below the x-axis. So those would all be on our list for our negative intervals from -infinity to -3. from -3 to 0, and from 5 to infinity. And you can actually put unions or commas there. I think in WebAssign, maybe they do commas. Either one is fine. Okay, and the last one from the day one review, we need to do a little polynomial long division. So we are going to divide this expression by this expression. The expression that goes under the division symbol, that's where we have to be careful that we are representing every power of x. We have 2x to the 4th minus 8x cubed, which means we need an x squared term, and we don't want to have one here, so we need to put a 0 in as a placeholder for x squared. Then we have our x to the 1st power, and then we have our constant. Out front, we do not have to worry about every power of x. It's only under the division sign, okay? The next thing we need to be concerned about when well, we'll get there in a minute. Let's just start. What do I multiply 2x squared by to turn it into 2x to the 4th? What do I multiply 2x squared by to turn it into 2x to the 4th? Oh, if you have trouble thinking through that, it's 2x to the 4th divided by 2x squared. Simplify that. The 2's cancel, and 2 of those x's cancel. It is x squared. So x squared goes up here on top. We then multiply down. You have to distribute it. You need to multiply it by both terms here. And when you do that, make sure you are writing the result in the column so that you get like terms. X squared times 2x squared is 2x to the 4th. By design, we made it that way. And then x squared times 6 is positive 6x squared. Notice I put it in the x squared column. I want to line up my like terms. If you want to put a 0 in there as a placeholder, if that helps, you can do that. Next, we have to subtract. We subtract each term, and that means changing our signs, okay? 2x to the 4th minus 2x to the 4th is 0. We made it that way. Negative 8x cubed minus 0 is still negative 8x cubed. 0x squared minus 6x squared is negative 6x squared. And then we drop down that next term, and we have our plus 12x. That was kind of one round. Now we're going to do it again. This time the question is, what do I multiply 2x squared by to get negative 8x cubed? Or if you like to think of it this way, negative 8x cubed divided by 2x squared, which is negative 4x if you cancel, simplify, reduce. So we need a minus 4x up here at the top. We're then going to, again, multiply it down, distributing it into both terms. So negative 4x times 2x squared is minus 8x cubed. Those should always match. That's the procedure. That's by design. Negative 4x times 6 is minus 24x. Notice I'm putting that in the x column so that I align my like terms. Then I'm going to subtract. So if we subtract a negative 8, that becomes addition. Again, you could put a 0 down here if you want, just so you're clear what's happening. If we subtract a negative 24, that becomes addition. The first two should always 0 out. Negative x squared minus 0 is negative 6x squared. Sorry, negative 6x squared minus 0 is still negative 6x squared. 24x and 12x gives me a positive 36x. And then I want to drop down that last term, minus 17. One more round. Now the question is, we move our way across, what do I multiply 2x squared by to get negative 6x squared? Or again, if you want to see it, negative 6x squared divided by 2x squared is negative 3. That's what goes up here at the top. Multiply it down, distribute it into both terms. Negative 3 times 2x squared is minus 6x squared. Negative 3 times 6 is negative 18. Then we want to subtract. That flips our signs around because minus a negative 6 is plus. Minus a negative 18 is plus. The first two 0 out. We get 36x. Negative 17 plus 18 is plus 1. Now in WebAssign, we wrote this kind of as all one continuous answer. Here it's asking separately for the quotient and the remainder. The quotient is the result after you've done your division. So our quotient is x squared minus 4x minus 3. And our remainder is, surprise, the remainder. So that is just 36x plus 1. It didn't ask for a single result where you take the remainder and put it over the divisor. So we just write those expressions as two separate answers, quotient and remainder.